My name is Alanda Kriener, and this is my lab number 5 Pick Your Own Adventure called the Umbrella Plunge. In this lab, I attempted to simulate a bungee jump with an umbrella and shoelaces in order to calculate the spring constant in the laces and the max tension at the bottom of the fall of the umbrella, where the force of the gravity equals the force of tension, aka the spring force. The physics principles I applied included Newton's second law, specifically the position and velocity update formulas, Hooke's law, which calculates the spring force using the spring constant and the length of the spring compared to its initial length times the L-hat vector, and the conservation of energy principle. In this experiment, the earth, the shoelaces, and the umbrella are all included in the system. Therefore, the total energy is zero, and components of potential spring and potential gravitational energy will be included in the final energy of the system. For the experiment itself, I dropped the umbrella tied to the shoelaces, as which you can imagine probably has some notable drag force on it due to the length and surface area of the object that I did not account for. I analyzed the video and tracker by establishing the axis and fully stretched length that I measured to be 19 inches or approximately 0.4826 meters. I also estimated the mass of the object to be around 0.7 kilograms by doing various internet searches, but is likely not extremely accurate. Tracker analyzed the point mass of the system from rest to the bottom of the drop, and here is the graph of the results, where the final position lies around 0.489 meters downwards. It's also important to note here that a shoelace does not accurately represent a spring because 1, it doesn't stretch that much, and 2, it doesn't really compress. So instead of the object oscillating up and down like a spring, it really only dropped down, and the length of the shoelace at the bottom of the drop differed from its resting length by a mere 0.0688 meters, or s. Next, I did some calculations to compare to a computational model that we will go into in a moment to estimate the spring constant of the shoelaces. Using the conservation of energy principle, I calculated that the potential gravitational energy at the bottom of the drop is equal to the potential spring energy of the umbrella, as you can see simplified here because the initial energy and final kinetic energy are both zero. Using my experimental data, I estimated the spring constant to be around 699 newtons per meter, which seems rather large, but it is sensible in the fact that the shoelaces were very hard to stretch. So now let's take a look at the computational model. I first input my initial conditions, such as the mass of the umbrella and the initial position and velocity of 0. I made sure to define the gravity constant, resting shoelace length, or L naught, stretched shoe length, or L, and S, the difference between them. Now I defined K of S here by 38 through trial and error of running the code and comparing the final y position of the computational model to the experimental model of 0.489 meters downwards. Additionally, for the while loop, I defined both the weight and spring forces using MGH and Hooke's law, and since shoelaces can't compress, I added an if-then statement for when S is less than 0, the spring force will consequently be 0 as well. Lastly, I defined the net force to be the sum of the weight force and the spring force, and I used Newton's second law to update the position and velocity of the umbrella. Here are the model results. As you can see, the y position of 0.486 downwards is very similar to the experimental position of 0.48 meters downwards using the Ks value of 38 in the model. I also wanted to compare the max tension forces of the model and experimental spring constant values, which would be the spring force at the bottom of the fall, so I calculated the spring force using the spring constant I calculated and the spring constant I estimated in the code. As presumed, the max tension forces varied drastically by about 45 newtons per lace difference. Now, obviously 699 is very different from 38. In order to do this experiment in the future to yield more accurate results, there are a couple things that should be done differently. First, I would use an object that I know the exact mass of with a definite shape that would minimize drag force, or I would account for the drag force. Importantly, I would also not use a shoelace again, but instead maybe a rubber band or something that functions more similarly to a spring. I would also drop the object from a higher distance and measure the resting and stretch lengths more carefully, hopefully seeing a much bigger S than 2 inches or 0.0688 meters. But I would apply the same physics principles such as the conservation of energy, Hooke's law, and Newton's second law to do my calculations. Thanks for watching.